All right, so what are we talking about today? We are talking about the nervous system, and there is a lot to learn about the nervous system because it's very complex. There's a lot in the nervous system. Um, so, where to begin? Well, we talk about in the notes, if you guys look on the notes, we talk a little bit about embryo development. It's one of the first things that develops in us is our nervous system and our brain. As you can see in you've got a very simple embryo, and what starts to happen right away is it sort of starts to invagulate or fold in. Let's just say that. Let's use that word. It starts to fold in. Infold. There we go. It starts to infold the tissue, and it makes this... This is a cross section that we're looking at, and it makes a tube basically that runs from the top to the bottom. The top of the tube is open. That's where the brain starts to develop, and the bottom of the tube there, that's going to be the spinal column. That's where all the nerves are going to run through, and the nerves go out into the periphery, and then they run up to the brain. There's also some nerves that run from the head face. There's actually 12 sort of main ones that run out of the brain, and 31 that run down out. There's 31 that run out to the body, and then they branch off out into the rest of the body. I think the best place to start with talking about the brain is just talking about a very simple system. Like, what does the brain do in its most basic form? And so some of you took Life Sciences 11, and we study flatworms in Life Sciences 11. Flatworms are they're the first organism, the most basic organism that shows cephalization. Cephalization means a brain. Now, they don't really have a brain. They have what's called ganglions, which are just bundles of nerves, which is kind of what the brain is anyways. But it's just, we have a lot more bundles of nerves in the brain. So how does a flatworm work? Well, what does the ganglion in the flatworm do? So if you imagine it's got two eye spots, and these eye spots, they don't see anything. They just sort of detect light and they detect dark. And so imagine you're a flatworm, and there's a light on this side, and it's flashing because something is moving. And the flatworm is like, I'm going to move over there and I want to eat that thing. Except it doesn't think any of that at all. Humans would think that, but flatworm, no. Because basic, at its most basic, what happens is this eye detects movement or detects a change in the light, so the eye on this side, and a nerve impulses go and stimulate the ganglions on this side. And the ganglion is sort of it'll be like, just like the brain, it relays. It, in a very primitive way, interprets the flashing as something that requires an action. And so the input comes in, and then that ganglion sends out an output on that side of the body, because the nerves go out. It's got the flatworms have like the ladder frame of nerves that go out, run throughout the body. And there's two main sort of nerve bundles that run, where we have 43, they've got two that run down the length of the body. And so I have movement on this side, input comes in on this side, ganglion sends a signal then out on that side, and that contracts the muscles on that body. And now I've turned towards the light. Most basic function. Your brain does pretty much the same thing. We receive inputs, our brain processes them, all those nerve fibers process them, and then the brain sends out action potentials for us to do something. Where we really differ from the flatworm is that processing. We have something called the cerebrum. The cerebrum, like Cerebro from X-Men, but cerebrum. Where's the cerebrum? Let me scroll through here. So cerebrum is this foldy bit. That's the big bit. That's us. That's where we process input and send out output. Right there in that cerebrum. And so the cerebrum holds memories and makes associations. So in the flatworm, very basic, flashing here, the association is movement, maybe food. but on a super duper basic level, so it does a squish towards the food. Whereas as us, it's a lot more complicated because we respond to language, to sound, to visual stimuli. We have all kinds of memories that we learn as we're children, but in a very fundamental way, we associate a lot of those memories. A lot of those things are either a good thing or bad, it's kind of binary. But if you lay over lots and lots of good and bad, good and bad, good and bad, it begins to become complex, the complexity of a human being. I use the example, I don't know if I talk about with you guys, but so when we're kids, our parents use our name. We learn our name, our first name. And so our cerebrum memorizes our name, learns our name, and associates lots of good things with our name, because it's usually your mom or your parent or whoever's taking care of you that says your name, and they're usually bringing you food. So it has a very positive association. People like to hear their name because they hear the sound of their name. Their brain has positive associations with their name. And so then it's the action potential is you want to move towards your name, or you want to smile, you feel good. It sends out a sort of feel good throughout your body when you hear your name. And one of the I work as a substitute a lot. So one of the things that I try to do is to say people's name correctly, or in a good way, because if I don't, I'm denying them that little feeling of good when I'm doing attendance and I say their name. And this is actually, there's been studies done on folks who are immigrants. Their names often change when they move to a new country. My name changed when I moved to Canada, for sure, and I know a lot of kids do. And so they're denied that little hit of positive feeling when attendance is done in school. And there's actually repercussions. There can be repercussions from that sort of, trouble in school. I mean, there's a lot more to it. It's a lot more complex than that, but it's one of the things. So interesting that way. But that's what your brain does: input and then output. And how does it do it? Okay. So you have, as you develop, you have a central nervous system. So that includes the brain and the spinal cord, and then it's connected to a peripheral nervous system. That's all the nerves that run off the spinal cord, and they're connected inside the spinal cord. Let me find there we go. So this is the central nervous system. This is a cross section of the spinal cord, and this is the peripheral nervous system coming in, and they're connected here. And so inputs are coming in the dorsal side, so that's your back, that's the back here. Inputs come in from the peripheral nervous system, so I sense hot, or I sense touch, or wet, or whatever. And then outputs go out this way. These are outputs, and then they go up the spinal cord, and then outputs go down this way and move the muscle, move you away from the hot, or move you towards the touch, or whatever it is. That's basically essentially the thing. Inputs this way, outputs that way. They go up and they go down. Okay, and there are 43 of these coming off. 12 of them are cranial, 31 are the rest of the body. And you see how they all connect. They run throughout the entire body. And we've got sort of the peripheral nervous system has two sections to it. It's got the autonomic nervous system and the somatic nervous system. The autonomic, you don't consciously, actually your cerebrum doesn't do anything with it. It's sort of the more animal part of your brain, the inside parts of your brain. So that's going to be the hypothalamus, the thalamus, those bits. Where is it here? If I can find a brain picture. So it's these bits, sort of the more inside. Your cerebrum is not dealing with that. Is not dealing with the autonomic nervous system. It's more your spine, more the animal, the flatworm parts of your brain. And basically what they're doing is stimulating the salivary glands to produce amylase when you're eating food, regulating your heartbeat, controlling the muscles in your stomach to churn the food in your stomach, all of those functions that are running in the background that you don't need to consciously control. So breathing, all those things needed to run your body are part of the autonomic nervous system. Then there's the somatic nervous system. It runs along, it's also part of the peripheral nervous system, and that's the bits that we control. So me moving my mouth right now is somatic. My tongue, though, going up and down and making the words is a little bit autonomic, isn't it? I'm not really controlling the specific movements of my tongue. So there's some crossing over there. Me just doing that with my hand, somatic nervous system. Etc., etc. Fight or flight is also in the autonomic nervous system. So that's when you have a shock, something happens and your body switches over and you get controlled by your autonomic nervous system. Then there's the brain. So the brain is the coordination center of your body. And so it's got sort of all these different parts to it. The corpus callosum, which connects the two halves of the brain, the thalamus, pituitary gland, cerebellum, and the cerebrum, the pons, and the medulla oblongata. Those are sort of the main ones that we're looking at. So the thalamus is the sorting center, which is basically inputs coming up the spinal cord, hit the thalamus, and the thalamus decides where they go. Do they go to the auditory part of your brain? Do they go to the visual part of your brain? Do they go to both parts of the brain? Do they go to the movement part of your brain, the sensation part of your brain? The thalamus is sorting those things out so they go to the right place. Visual stimuli goes to the visual part of your brain. It goes to the part of your brain that recognizes faces, maybe, all those things. The hypothalamus. This is where this is part of the autonomic nervous system. It controls homeostasis. So we talked about this when we were talking about blood pressure and stuff. So it detects, it detects if your blood pressure is too high, blood pressure is too low, and it controls your body with hormones, and it sends out hormones from the anterior and posterior pituitary glands, and it's connected to the anterior. I'm going to get it wrong, so I'm not going to say it. It's connected one way with nerves, but it sends hormones along those nerves, and then the other way it's connected with very short blood vessels. And so the hypothalamus makes a hormone, and that hormone just travels a very short way to the pituitary gland that then activates the actual hormone that then will go and target the specific organ that the hypothalamus wants to control. So make the heart beat faster, make the liver do more livering, that sort of thing. Like I said, it's part of your autonomic nervous system. We don't control the hypothalamus. It's deep here in your part of your brain. There's this sort of all the things that the anterior and posterior pituitary glands control. Okay, medulla oblongata. So this is your real animal brain. It's at the top of your spinal cord. There it is. And it's before your brain, basically. And so it's doing a really important job. Number one, it's the respiratory center. So it's monitoring CO2 and H plus in the plasma. Remember we talked about it in respiration. So if CO2 concentration goes up, your medulla oblongata goes, I gotta breathe more because we're making too much CO2. CO2 is toxic. Let's breathe that CO2 out. Bring more O2 in. So that's your medulla oblongata. Your brain doesn't even play into that because respiration is so important that your brain doesn't matter. If you're not breathing, your brain it doesn't matter. It doesn't matter because your brain is dead. So it supersedes your brain. The other thing that it does, it's the reflex center. So it's sort of protecting your body from dangers. The most traditional example is you put your hand on a hot stove. Pain receptors in your heat and pain receptors in your skin send a huge signal, a huge potential gets sent up your arm. The potential is so big that before it makes it even to the brain, it triggers the medulla oblongata, which immediately sends a signal down the corresponding motor nerves to contract the muscles so you pull your hand away. Totally uncontrolled move. It's a reflex arc. Your brain had nothing to do with it. It's to protect your body. So dog bites you, you will move away your arm and it'll actually rip your flesh. You have to overcome it if you don't want to rip your flesh, that sort of thing. That's what the medulla oblongata does. It's your most basic animalistic brain. It's your flatworm brain. Next. So then there's the cerebrum. We talked about that. That's the thinking center. So, it's so complicated what the cerebrum does, and we still don't know all the things. But for example, I use this example. So you see a candy bar. So all the things that the cerebrum will do, it'll access memories to associate. It'll remember the taste of the candy bar if you've had it before. It'll remember whether you like it, the name of the candy bar. It'll remember the letters in the wrapper so you can read the name. And it'll associate those letters into a word, then associate them into a candy bar, then remember what's in the candy bar. Is it nougat? Is it chocolate? All those things. And that way it'll, all those things, it basically remembers all those things. So, Three Musketeers, I don't know, that's used to be my favorite candy bar. So it's got nougat and chocolate. I'll remember all those things. You remember the flavor of that, and you are able to then, based on that, make the decision of, do you eat the candy bar, do you not eat the candy bar? The cerebrum is also remembering, especially, for us older folks, is remembering, candy bars are bad. You're going to gain weight. There's a cost of it. All of that stuff is being processed by your cerebrum. It's the thing that makes us human, if you think, because it's so complex and it stores so many memories and makes so many connections with those memories. It's quite amazing. And it goes good, bad, but ultimately it decides this is a good thing, this is a bad thing, this is a good thing, this is a bad thing, and all those little good things, bad things add up to you making a decision to do something. Cerebellum is, this is the part of your brain which you definitely don't want to damage. It monitors body orientation in space to provide balance and coordination. So folks like athletes, gymnasts, dancers have a really developed actually cerebellum because they have to know where their body is in space. This is a part of your brain you actually train. When you're a little kid, you're training your cerebellum to learn where your body is in space so that you can walk and you can be upright. People who are in car accidents sometimes, or they take a really bad fall, the cerebellum is here at the back, you take a back fall, boom, shock in your cerebellum and damage your cerebellum, is a real big problem because it affects balance and it affects walking, and you definitely don't want to damage your cerebellum because it's well, you don't want to damage any of your brain, but the cerebellum, I don't know, for some reason it really freaks me out. And it receives signals. Your cerebellum receives signals from something called proprioceptors. They're located throughout your body, and they send little tiny signals constantly telling your cerebellum where your limbs are. That's where these proprioceptors are. So even though I'm not looking at my arm, I know where it is in space. If you damage your cerebellum, or you damage your proprioceptors get damaged, you actually, folks don't know where their arm is in space. They don't know where their body is in space. Astronauts that actually go up to the space station, there's one of the side effects is because they're floating in space, all these things get affected. So they have trouble figuring out where their body is in space. They learn very quickly, but it's one of the side effects. Okay, corpus. Then we have the pons. The pons, again, it's at the top of your spinal cord. Where is it? Pons. Show me pons. Show me pons. I think I've gone too far. Sorry. Pons. There it is. Pons. Pons is sort of the filtering center. So our periphery nervous system is constantly sending data. And your cerebrum would get overwhelmed with all the data that it's being sent by your peripheral nervous system, right? I mean, I'm moving my hand, it's rubbing against the air, the skin here is rubbing against the skin, my clothes are rubbing against me constantly, rubbing on me, pulling on my flesh, pulling on the little hairs in my body. My feet, as I'm walking, your feet are ground into your shoes and into your socks. There's a lot of signal coming from that. What your pons does, it basically, the signals that are repeated over and over and over and over and over and over and over again, that are, the same signal over and over again, your pons says, We got it. I gotcha. Yep. Grinding your feet into your shoes, and there's nothing we can do about it, so I'm going to filter that out so your cerebrum doesn't get overwhelmed with those signals. Again, astronauts, good example of pons sort of activity. There was an astronaut a couple years ago, just 2 years ago, a year ago. He went up to space. He went up for a year. He lived on the space station for a year. One of the longest stays of anybody. There was two of them. It was a Russian guy and an American guy. The longest stays that astronauts have done in zero gravity in space. And Kelly, his last name was Kelly. Anyways, when he came back, so when you're floating in space, your clothes are no longer, gravity's no longer pulling them on you. They're floating above you. Your clothes are always kind of floating above you. Your shirts are floating above you, and you're never grinding your feet into the ground. Your feet aren't touching the ground. And when he came back, he said it took months for him to stop feeling the sensation of his clothes, the itchiness of his clothes rubbing on him, and to stop feeling the pain of walking and the pain of your feet being crushed by your weight in your shoes. So because his pons had de-learned, they weren't receiving those signals anymore, and all of a sudden those signals were treated as new signals, and it took a couple months or weeks for the pons to be like, okay, this signal, we're getting it over and over and over again, let's just ignore that signal. Okay? Next, last sort of bit is that we want to know about is the corpus callosum. I mean, there's lots that we want to know about, but let's just stop on that. So corpus callosum, and it connects the two hemispheres of the brain. So the brain is, divided in two. Here, this is a slice through the two hemispheres. Is there a nice picture? Did I include a nice picture of the two hemispheres of the brain? Well, you've all seen it. We don't. There we go. So there's one hemisphere and another hemisphere. We're right-brained, left-brained. I think a lot of that's been discredited. Anyways. The corpus callosum is a huge bundle of fibers that connects the two. Interestingly, you don't need it. People can live without the corpus callosum. So there's a birth defect where kids are born without the corpus callosum, and depending on a whole bunch of things, they can be just completely fine, totally normal. And we actually still to this day, there's a medical procedure to cut the corpus callosum. This is in folks who have debilitating epilepsy, where they have a seizure every minute, that they can't concentrate, they can't focus, they can't function in normal life because they have seizures so often. What one of the treatments is, when their medication doesn't work, or seizure suppressant medication, any of that stuff doesn't work, one of the treatments is to finally cut. So the patient's head is shaved, head is peeled, skin is peeled, skull is opened, and very carefully, this would be one of those, procedures that probably takes many, many hours. My mom worked at BC Children's Hospital as a brain, she wasn't a surgeon, but she was a brain, monitoring ECG technologist, there we go. Anyways, so she would participate in these huge multi-hour surgeries on kids. Well, anyways, one of these, so they can cut the corpus callosum, because epilepsy is like a short circuit. Things are being sent between the brain when they're not supposed to be, and so that that signals are being sent to the periphery that causes these seizures. So cutting the corpus callosum somehow can stop that from happening, or at least reduce it to a level where a person can live a normal life. And cutting the corpus callosum, the side effects are often minor or none at all. Some of them include where, like me right now, people have trouble speaking. So they have a thought, but it can't connect the right way. And so it takes them a while to get the words out. They can have phantom limb or phantom hand syndrome, where their hand does things on its own, or it feels like it's doing things on its own because this part of the brain's not connected to this part of the body anymore. And there can be numbness and tingling in the extremities, that sort of thing. Okay, so that's sort of a primer on the brain. something for you to think about. I don't have an assignment. I don't have a thing. Read through this. There's a video. There's a big, an hour and 26-minute NOVA video. It's just very interesting. It's for your interest. You don't have to watch it. You guys probably won't. But it is extremely interesting video on how the brain works and processes stuff and how it can be tricked and things like that. What else is on here? There's just a video of the development of the central nervous system that's very short. So we'll just watch that so you can see what that looks like. I don't have an assignment yet for this, but one will be coming soon, of course. So for now, go over these notes, go over those questions in the workbook so that you start to understand these structures and what they do. Okay, well done.